Hello folks, welcome to the next episode of Physics GRE Lectures. I'm your host Rev Bari, Brown University physics grad student. Today I'm going to derive the Biot-Savart Law. It helps you find the magnetic field due to an arbitrary current distribution at some distance away from the current distribution. So what does that mean? I might have said a bunch of gibberish that might sound strange, but let me explain what we're going to do today. Basically, if someone gives you some charge distribution, okay, let's say that charge distribution is given by this charge density, how can you find the electric field due to that charge distribution? That's the whole question of electrostatics. Well, the answer is first you find the electric potential from the charge density, and then from the electric potential you find the electric field. How do you do that? Well, if you have some charge density, some charge distribution given by rho of r prime, then of rho of r. By the way, r is the distance away from the origin. So for example, this is r, the r vector, or r prime rather. So this should really be r prime. So if you're given some charge distribution, rho of r prime, how can you find the electric potential and then the electric field? Well, you can find the electric potential by solving Laplace's equation for the electric potential. And the solution to Laplace's equation is that you just integrate over the charge density divided by however far away you are from the charge distribution. Okay, so even if you don't see this entire formula, the basic idea is we just integrate over this charge distribution, right? So we just add up the electric potential due to each tiny piece of this charge distribution, and then we get the total electric potential. And then once we do that, we can find the electric field by just taking the negative gradient of that electric potential. So that's the name of the game when it comes to electrostatics. That's all of electrostatics in 2 minutes. How do you play the same game with magnetism? How do you find the magnetic field due to an arbitrary current distribution? So here's how you do it. So if you have some kind of a current distribution, some kind of a current carrying wire that's carrying some kind of a current I, how can you find the magnetic field at some point P that's some distance r prime away from any part of the wire? And this point P is a distance r away from the origin. Okay. Well, you do it by using the Biot-Savart law. Okay. So what does the Biot-Savart law tell us? So essentially, we start with some kind of a current distribution given by this current density. And then from the current density, we can find the magnetic vector potential, call that A. And then from the magnetic vector potential, we can find the magnetic field, call that B. Okay, just like we did analogously with electrostatics, right? From rho of r, a charge distribution, you can get the electric potential. From the electric potential, you can get the electric field. Okay, so what's the connection between the charge density and the electric potential? It's Laplace's equation, isn't it? That the Laplacian of the Poisson's equation tells us the Laplacian of the electric potential is minus rho over epsilon naught. And then to get from the electric potential, so once you solve this, you get that the electric potential is just essentially integrating over the charge density divided by the distance to the charge distribution. And then once you get that, you can get the electric field by taking the negative gradient of the electric potential. We play the same game with magnetostatics, with magnetism. You start with some current distribution. You can find the magnetic vector potential by solving Laplace's equation for the magnetic vector potential now, right? So this is Laplace's equation for the magnetic vector potential. And then once you get the magnetic vector potential, you can find the magnetic field by just taking the curl. So that's the basic idea. Now, how do you actually put that into practice? You put that into practice by using the Biot-Savart law. So how does the Biot-Savart law work? The Biot-Savart law, which I will derive right now, tells us that the magnetic field is at some point P. So let me write this. Magnetic field at some distance r from the origin is mu naught I over 4 pi times the integral of this cross product dl cross into r hat prime divided by your distance from the current distribution squared. And then you integrate over the current distribution. So let me try to explain what this is saying. First of all, let's go to this step by step. B of R, that tells us this is telling us the magnetic field at some distance r from the origin at point P. Okay, mu naught over 4 pi, this is just a constant. Where does this constant come from, you might ask? It comes from Ampere's law. So this 4 pi actually comes from the surface area of a sphere, and this mu naught comes from the mu naught in Ampere's law, which is that the curl of B is mu naught J. Okay, essentially integrating Ampere's law gives you this mu naught I. Okay, and this 4 pi comes from that integral measure over the surface area of a sphere. Essentially. Of course, it's a bit more tricky than that, but that's the basic idea. What is this dl vector here? This dl vector is a small step along your current carrying wire. That's that dl. What is this r hat prime? This r hat prime is a unit vector from where you want to find the magnetic field to your source, to your current source. So this is your r hat prime vector. And this r vector minus r prime vector squared is just a distance squared to your source. And then we just integrate over the source current. So basically what the Biot-Savart law is doing is it's chopping up this wire into many small pieces. So it's chopping up this big wire into a lot of small tiny wires. And then it's finding the magnetic field. Let's call this small magnetic field dB1, D for a small differential magnetic field. Let's call this dB1, call this dB2, call this dB3, okay, so on and so forth. You find the magnetic field due to each one of these small parts of the wire. And then you can add up the magnetic field along each one of these tiny parts to get the total magnetic field, B, due to the entire wire at this point P. Okay, so that's really what the Biot-Savart law is doing. It's slicing and dicing. It's slicing up your current carrying wire into lots of small tiny parts, finding the magnetic field contribution at point P due to each of these small tiny parts, and then it's adding up all of those small tiny parts to get the total magnetic field at point P. So now that we've seen what the Biot-Savart law can do, is there a way we can derive it? And the answer is yes. So we can derive the Biot-Savart law, and that's what I'll be doing right now. So to derive the Biot-Savart law, here's how we start. We start by writing down Maxwell's equations. So we have the divergence of the electric field proportional to the charge density. This is just Gauss's law. We have Faraday's law that says if you tickle the electric field, you give rise to a magnetic field. We have Gauss's law for magnetic fields, which says there cannot be any magnetic monopoles. And then we have Ampere's law, which tells us that the curl of the magnetic field can help you find the magnetic field due to some arbitrary current distribution. 1 over c squared. It also tells you if you tickle a magnetic field, you give rise to an electric field. So if we look at Maxwell's equations, we can figure out the answer to both electrostatics and magnetostatics just by looking at these. To find out the answer to electrostatics and magnetostatics, the first keyword is statics. Statics means that nothing is changing over time. So if you don't have a magnetic field that's changing over time, or an electric field that's changing over time, this is 0, and this is 0. So Maxwell's equations immediately become a bit simpler to look at. So this right here tells us that the curl of the electric field is 0. This tells us here curl of the magnetic field is just proportional to the current density. Now we look at these and we see, is there anything we can extract from these? Well, yes, in fact, there is. The curl of the electric field being 0 immediately tells us that the electric field can be written as the gradient of a scalar potential. This is just calculus 3 knowledge. If you have a vector field whose curl is 0, whose curl is 0, then you immediately know that vector field can be written as the gradient of a scalar field. Now you can use that knowledge to write E, the electric field here, as the negative gradient of V. So you can rewrite the first law, the Gauss's law, as a divergence of, let me put vector signs over all of these. The divergence of the gradient of V is rho over epsilon naught, right? It just comes from here. But the divergence of the gradient, what is that if not the Laplacian? So this right here tells us the Laplacian of V. Negative Laplacian of V is rho over epsilon naught. So that means that the Laplacian of V is minus rho over epsilon naught. This right here is Poisson's equation for the electric potential. Okay, so this is so important that we give it a name, Poisson's equation for the electric potential. Now we can play the same game with magnetic fields. Of course, we're going to solve this equation in a minute, but just give me a minute. Let's first get the same equation for magnetic fields. Looking at the divergence of B is 0, we can immediately recognize that tells us that B, the magnetic field, can be written as the curl of an arbitrary vector field. Let's call it A. So this is actually called, this A is called the magnetic vector potential. Okay, and it basically, the fact that there's no magnetic monopoles allows us to express the magnetic field as the curl of this magnetic vector potential. So now we can take this newfound knowledge and plug it into here. So if we look at what the curl of B is, we now know that B is nothing more than the curl of the magnetic vector potential. Now it's a vector identity that the curl of the curl is the divergence of, it's the gradient of the divergence of A minus the Laplacian of A. Now notice that since B is just the curl of A, I can choose the divergence of A to be anything, right? So why not choose it to be the simplest possible thing? Why not choose the divergence of the magnetic vector potential to be 0? This right here is called the Coulomb gauge. Why is it called a Coulomb gauge? Because we can choose the divergence of the vector potential A to be anything. So why not choose it to be the simplest thing, 0? If we choose the divergence of A to be 0, this term here is 0. And so we obtain that the curl of B, okay, the curl of B, curl of the magnetic field, is equal to the negative Laplacian of A, magnetic vector potential. So now we can come back to Ampere's law for a static situation and replace the curl of B with the negative Laplacian of A. Moving the negative to the other side, we get that the Laplacian of A is minus mu naught J. So now we've obtained Poisson's equation for the magnetic vector potential. So you see we've got a Poisson equation for the electric potential and a Poisson equation for the magnetic vector potential. So now the question becomes, how do you solve Poisson's equation to extract the electric potential from this? Well, the answer is pretty straightforward. Hopefully you might see if I write there, you might not. So let me instead write over here. Let's erase all of this and just leave the Poisson equations we've derived. Okay, so here is Poisson's equation for the electric potential. Here it is for the magnetic vector potential. And so now let's try to extract the electric potential from this guy over here. How do we do that? Well, we look at this. We look at this for a moment. And then we think, what's the simplest solution to this? What's the simplest solution to this equation? Well, it's the Green's function. The Green's function of the Poisson equation should give us a delta function solution by definition. Okay? But what kind of electric potential gives you a delta function for your charge density? There's only one kind of charge density over space that can give you a delta function. Okay? What is that? It's a point charge. a point charge, let's say it's at the origin, but a point charge Q creates a delta function charge density, right? There's no charge, no charge, no charge. Suddenly there's a point charge, no charge, no charge. That's a delta function. So that means the Green's function for the electric potential equation, the Green's function, remember, is that function which is defined to give you a delta function output for your differential equation. The Green's function for this Poisson's equation is just the electric potential for point charge. So that means the Green's function here, G of R, is 1 over 4 pi epsilon naught Q over R, where R is the distance to the origin. But that means we can create an arbitrary solution, an arbitrary electric potential for an arbitrary charge distribution by just adding up the Green's function solutions, right? So if we have an arbitrary charge distribution, I'll just draw it here. If we have some arbitrary charge distribution, rho of R, that's just made up of a lot of point charges. So if we basically add up a lot of delta functions, we get an arbitrary charge distribution. Likewise, if we add up all of our Green's function solutions, we get the solution to an arbitrary charge distribution. We get the electric potential for an arbitrary charge distribution. So that means the electric potential, V, for an arbitrary charge distribution is just the sum of all the Green's functions. You just integrate 1 over 4 pi epsilon naught rho of R prime divided by the distance to the charge distribution, and then you just integrate over the volume of the distribution. So this is the solution to Poisson's equation for the electric potential. Now how do we solve it for the magnetic vector potential? Play the exact same game. Now we can actually just, to solve this magnetic vector potential equation, we just replace the electric potential V, hopefully you'll see what I write here, with A, and we replace the charge density with the current density. That's it. So actually, maybe I'll write it over here. So that means the solution to the magnetic vector potential is A is 1. Well, actually, it should be mu naught over 4 pi, because mu naught shows up in the numerator here. Mu naught shows up in the numerator here because, remember, Ampere's law says the curl of B is mu naught J, whereas Gauss's law says the divergence of E is rho over epsilon naught. That's why mu naught is on the top for magnetic fields, but epsilon naught is on the bottom for electric fields. So our solution is mu naught over 4 pi. Just replace the charge density with the current density. And this current density is a vector, unlike the charge density. And we divide it by R minus R prime. That's the distance to the source. And then we just integrate. So voila. That's how you find the magnetic vector potential due to a source, due to an arbitrary current source. But what about the magnetic field? At the end, we just want the magnetic field, not the magnetic vector potential. Well, now that we have the magnetic vector potential, we can easily get the magnetic field by taking the curl. B is the curl of A. So that means the magnetic field is the curl of this integral, mu naught over 4 pi J of R prime divided by our distance to the current carrying source, and then integrate over the source. Okay, so let's erase all of this. Okay, but now we can actually use a vector identity to simplify this. Turns out that the curl of J of R prime divided by the distance to the source is equal to the cross product of our current distribution, J of R, multiplied by R minus R prime divided by R prime cubed. Now this may look foreign to you, but actually this is not too bad. Let's bring this over here and rewrite that second term in the cross product as R minus R prime divided by the magnitude of R minus R prime, and then times 1 over R minus R prime squared. Now this over here, let's say that for simplicity, we're looking at we want to find the magnetic field at the origin. That means R is 0. So that means this right here is just a unit vector r hat prime. Remember, r hat prime is the distance to an arbitrary point on your current distribution. So that means, and by the way, okay, let's keep going. This is j of r prime crossed into r hat prime divided by r minus r prime squared. Now j of r prime, we can rewrite this as what? Well, this is the charge density, which is the same thing as the current times a small section of your wire, I times dl. So now our final equation is starting to take shape. So this is equal to I, the current, times dl, a small section of your wire. This is like dl. This is like the dl vector. I dl crossed r hat prime divided by the distance to your current distribution. So that's what the curl of this thing is. So now we can just plug in what we just found into our equation for the magnetic field, and we find that the magnetic field B at some distance r from the origin is, we've already taken the curl of this integral. This is what we got. Okay, we've got our mu naught over 4 pi. Let's bring out our I over here. It's just a constant, times the integral of dl crossed into r hat prime divided by our distance to the source. And this, ladies and gentlemen, is the Biot-Savart law, which helps you calculate the magnetic field due to an arbitrary current distribution at some distance away from the source. So thank you for watching. We'll see you in the next one.